All right, welcome to lesson 3 of module 5, linear functions and proportionality. And so we're going to continue on this vein. In the last lesson, we defined functions in this way. We said a function is a rule that assigns to each input exactly one output. And so we used this diagram here of a function box or a function machine. And we said that we can have input, and in this situation here, time is our input. So if we put time in, then this function d here is going to kick out the distance traveled in t seconds. So every time I put 2 seconds in, I should get the same thing out. So that's where this part. Each input has exactly one output. All right, and so we used this for the distance that a stone traveled as it was dropped from a height. And we saw that that was actually kind of a complicated non-linear equation that defined that rule, but that it was a good predictor. So we want functions to be able to predict things for us. So that's why we have to be able to trust that every time we put a particular input in, we get the same input out. And there's only one thing that could come out for that. So here is an example that you had in the problem set of lesson 2. And this is a table of inputs and outputs for a function. And so we're going to use bags of candy, number of bags of candy as our input. Total cost would be the output. So there's a rule that tells me if I input the number of bags of candy, this rule tells me what the cost is. Okay, so I can see that this is a function because it's for every input, I have exactly one output. I'm not putting 2 bags of candy in twice and getting something different out. So I know that it's a function, and so in this lesson we're going to be talking about linear functions. So I could say, is this a linear function? Okay, so what would a linear function be? Well, it would have to be a function that would be defined by a linear rule, right? So the rule that assigns the cost to the number of bags of candy would have to be linear. So we saw that linear functions have a constant rate of change. So I could look at the rate of change in this function. I could see that when I go from 1 bag of candy up to 2, it goes from $1.25 up to $2.50. So the change is $1.25. That's the increase there. When I go from 2 to 3, I get the same $1.25 increase. So every time I go up 1, it goes up $1.25. So what this tells me is that I can write a rule here that the total cost y is equal to $1.25 times the number of bags of candy. So that's my function rule. And we've seen this a lot. This is in the form y is equal to mx plus b. So any linear equation can be written in that form. So we've done that with this one. We've said y is equal to 1.25x. And we can check each of these ratios here. So we can check, for instance, $6.25 is the total cost for 5 bags. So that's $1.25 per bag. And every one of these XY pairs is going to check out with that constant rate. And so if we graphed it, we would get something that looks like this. And you can see that it's that it's linear, and so we can see each of these is going to reflect that $1.25 increase for each bag of candy. So there's there's a couple things that we want to notice from this function. And one thing is that we can write a function statement. So we could say that the total cost is a function of, and we're going to be using that statement a lot, is a function of, total cost is a function of the number of bags purchased. Okay, so my total cost depends on, or is a function of, the number of bags purchased, number of bags of candy. So on this graph, we haven't connected the line, and there's a pretty good reason for that. Let's write our function rule. We've got total cost is equal to $1.25 times the number of bags. We've got some restrictions on x. What can x be? Well, x is an integer. The reason for that is we can't buy fractional bags of candy. We have to buy whole bags. 1, 2, 3. We can't buy 2.5. It's not sold that way. So x is an integer, and also we can't buy negative bags of candy, so x has to be greater than or equal to 0, and so that means y is also going to be greater than or equal to 0. So when we have these functions, we're going to have some kind of description. Something is a function of something else. We'll often have a function rule. In this case, we do have a mathematical rule for this. And then we might have some restrictions on x and y. Okay, another thing to notice is that this graph probably doesn't represent all of the inputs and outputs for this function, and neither does this table, because we might be able to buy more bags of candy. So it, this function has this graph and table of values, but it's not complete, but it does show me kind of what's going on with the function. Okay, let's look at a different function. In this example, okay, so Walter walks 8 miles in 2 hours, and so we're asked what is his average speed. And so Walter's average speed is his total distance, 8 miles, divided by his total time, 2 hours. So he goes 4 miles per hour. So if we want to assume that that's his constant speed, that if over every time interval he's going 4 miles per hour, then we could write this equation that relates his distance to his time. And we could say y is the distance traveled in x hours. So the total distance is 4 times the number of hours that he walks. X would be hours. And then in function language, we could say that his total distance is a function of the time spent walking. And so the input would be the time, the output would be the total distance. And in this example, we'd have limitations on x and y. We can't have negative amounts of time. So x has to be greater than 0. And since x is greater than 0, y is going to be greater than 0 as well. Okay, so let's look at example 3 now. Veronica runs at constant speed. The distance she runs is a function of the time she spends running. Okay, so see that is a function of. So this description's already given for us. The function has the table of values shown below. So if she runs for 8 minutes, she goes 1 mile. 16 minutes, 2 miles, and so on. So my question is, what is the equation that defines this function? Okay, so here we have inputs of time, output of distance, and we know that this is constant speed, therefore it's a linear function. So we should be able to write an equation, a linear equation that would define it. So go ahead and think about what that would be, and you can pause the video if you need to. Okay, so we know that if she goes 1 mile, that's her, if her distance is 1 mile, it takes her 8 minutes. Okay, so her average speed, or her rate, is 1/8 of a mile per minute. I could put that in decimal form, but generally we want to leave it as a fraction because the slope is pretty meaningful as a fraction like that. So we could check each of these pairs. 2 divided by 16 is 1/8, 3/24, and 4/32. So all of those are. And so that's the function. So the function would be then that her total distance, y, is equal to 1/8 times the amount of time in minutes that she spends running. So we could check that if we put in 8 for x, 1/8 times 8 gives us 1. If we put in 24 for x, 1/8 of 24 is 3. And so this function works. When we did this in class, a lot of people weren't sure if this should be 8 or 1/8. So it's always good to just double check with your table of values when you're writing a function like this. Okay, and so again, this is a y equals mx plus b. Of course, b is 0. M is the rate, 1/8 of a mile per minute. So y equals 1/8 x. And again, this is a time, and so x is greater than or equal to 0, and y is greater than or equal to 0. Distance and time have to be positive. Okay, so example 4 shows us a different example of a function. Time is still the input, so you can come look down here for a minute. Time is the input, but volume of water is going to be the output. So let's read about that. Water flows from a faucet at a constant rate. That is, the volume of water that flows out of the faucet is the same over any given time interval. So constant rate implies a linear function. If 7 gallons of water flow from the faucet every 2 minutes, determine the rule that describes the volume function of the faucet. So we know that we could write a rate. So I like to think of what are my units going to be on my rate before I write it. So it's going to be gallons per minute. So how many gallons flow out in any given minute? So we've got 7 gallons in 2 minutes. So we have this rate of 3.5 gallons per minute. So every minute, 3.5 gallons is coming out. So I can write the rule using that rate, so I know that y, which is the total volume of water flowing, is equal to 3.5 times the number of gallons. So I should write that. So I should say define my variable where y is total volume flowing, total volume, I'm going to run out of room here. This pencil's hard to write with. Total volume of water that flows, let's just say that flows in X minutes. We have it in minutes here. Okay, so there's my rule. This is a linear function, a linear rule, because we have constant rate. We're assuming that every minute it's 3.5 gallons flowing out of that faucet. Okay, so if we wanted to fill a 50-gallon tub, could say, well, how long would that take? You know, how many minutes would it take to fill a 50-gallon bathtub? Now, we're not down on this part yet, so don't read the next part. So I'm going to give myself some space here. I'm going to erase my my variable definitions here. But I know that y is gallons and x is minutes. And so I want to know how long for 50 gallons. So 50 gallons is equal to 3.5 times the number of minutes that that the faucet is on. So if I want to solve for x, then I just need to divide by 3.5, divide by 3.5. And what I find is that x is about 14 minutes. So in about 14 minutes, this tub is going to be full if I have 3.5 gallons every minute. Okay, so now let's look at the second part of this example. Now assume that you are filling the same tub, volume of 50 gallons, with the same faucet, a faucet where the rate of flow is 3.5 gallons per minute. This time, however, the tub already has 8 gallons in it. Will it still take 14 minutes to fill the tub? Explain. Okay, so obviously it won't take as long, right? Because there's already some water in the tub. So let's see if we can write a function rule for this situation where there's already some water in the tub, and then fill out the table below. So if we had y is equal to this flow rate, 3.5 gallons per minute times the number of minutes, but the tub already has 8 gallons in it. So I want to add the 8 here, because remember y is in gallons, and so we already have 8 gallons here. So we've got a head start. So we don't need quite as much water to flow to get the tub full. So how long will it take now that we already have 8 gallons in it? So I could use the same thing. I'm going to put in 50 for y. I'm going to change back to purple here. So put in 50 for y, 50 gallons, is equal to 3.5 x plus 8. So if I subtract 8 from both sides, I get 42 is equal to 3.5 times x. And then x would then equal 42 divided by 3.5. So x is equal to 12. And so 12 minutes. It's going to take 12 minutes for the faucet to fill a 50-gallon tub when 8 gallons are already in it. So the table of values that represents this situation is right here. So at 0 minutes, the tub has 8 gallons in it already. At 3 minutes, I would just put it into my function here. 3 times 3.5 plus 8 would be 18.5. So 18.5 gallons. And then at 6, we've got 6 times 3.5 plus 8, which is going to be 29. And on these problems, if you'd like to use a calculator, that would be fine. The important thing here is figuring out what's going on with these functions, not the actual multiplication. So 9 gallons, or 9 minutes, I'm going to have 39.5 gallons, and at 12 minutes, I'll have the full 50 gallons. So our function description for this situation would be that that total volume in the tub is a function of the time that the faucet is running. So total volume of water flowing is a function of time. Okay, here's our last example before we get to the exercises. And this one again is about water flow. So here we're given a table of values, and we're told that water flows from a faucet at a constant rate. Assume that 6 gallons of water are already in a tub by the time we notice the faucet is on. The information is recorded as 0 minutes and 6 gallons of water in the table below. The other values show how many gallons of water are in the tub at the given number of minutes. Okay, so can you write a function rule that would reflect the constant rate of this faucet, which is going to be different from the other faucet, and that would express the function of the total volume in the tub as a function of time that the faucet is on. Okay, so in order to find the rate that this water is flowing, we have to look at some of these points. So we can see here that between 0 and 3 minutes that a certain amount of water flowed. So in 3 minutes, the water, in 3 minutes, we had this much. We had 9.6. It went from 9.6 up to 6. So if we subtract, we can see that 3.6 gallons of water flowed in 3 minutes. So we have 3.6 gallons in 3 minutes. So that's 1.2 gallons per minute. Okay, and we could do that. It would be good to check that with another data point. So let's do this one. So between 5 and 9 minutes, it went from 12 to 6.8. So 16.8. Sorry, 16.8 minus 12 is 4.8 gallons. So we had 4.8 gallons, and between 5 and 9, that's 4 minutes. So remember, this is this is showing constant rate, isn't it? 1.2 gallons per minute again. Okay, so we want to write a function rule for this situation. So I'm going to get a blank piece of paper. So we know that the total volume, Y, is going to be however much is flowing out in a given number of minutes. So that's going to be 1.2 times x. So our rate times the number of minutes, plus we already have 6 gallons in the tub. Let's go look back and check that. So we'd want to calculate for the number of minutes. 3 times 1.2 would be 3.6, plus 6 would give us the 9.6. Okay, so that's our function right there. Multiply by the 1.2 and then add 6. So there's our function rule that reflects the water that's already in the tub. So if the tub was empty, then we would just get rid of the plus 6 and it would just be y equals 1.2x. And we could talk about restrictions on x and y. Again, x is time, so x is greater than or equal to 0, so y is greater than or equal to 0 in these functions. Okay, so let's go ahead and go to exercises 1 through 3. You could attempt to do these independently and then come back and check them or check them against the answer key. You could go ahead and pause now and do that, and then come back and I'm going to talk through these just so we're really clear on what the expectation is for the problem set here. But notice we're not learning a lot of new math concepts, but we are learning some vocabulary. So these exercises are going to try to cement some of that vocabulary that we're learning. Okay, so a linear function has the table of values below. The information in the table shows the function of time in minutes with respect to mowing an area of lawn in square feet. So we want to explain why this is a linear function. It's going to be a linear function if the rates are constant. So it's a linear function if the rate of mowing is constant over any time interval. So is constant over all time intervals, we'll say. Over all time intervals. Okay? And these next couple of exercises are going to walk us through that constant rate. So let's look at that. First let's describe the function though in terms of area, mode, and time. Okay, so we could say that the area mode is a function of the number of minutes spent mowing. Okay, so once again, the area mode is a function of the time spent mowing. Okay, so the input is time, output is the amount of area that gets mowed. All right, so let's look at some of these rates. So what is the rate of mowing a lawn, mowing this lawn, in 5 minutes? Well, in 5 minutes, we could mow 36 square feet. So we would have 36 square feet per 5 minutes. And if I simplify that or do the division, I can see that that's 7.2 square feet per minute. All right, so let's look at the rate of mowing the lawn in 20 minutes. So in 20 minutes, 144 square feet got mowed. So this is going to be 144 over 20, which again is 7.2 square feet per minute. Okay, we can do the same thing for 30 minutes. I'm going to go back and find the data. 30 minutes is 216, and 50 is 360. Okay, so there's the computation on the rate over the 30-minute interval and the rate over the 50-minute interval. Okay, and so in part G, we want to write the rule that represents the linear function describing the area in square feet mode. Y is the area mode in X minutes. So what I'm going to do, I'm going to kind of write this function backwards. So I've got 7.2 feet squared per minute times the number of minutes, and that's going to give me my total area mode. So Y is the square feet mode, and then 7.2 is the rate, and then X is the time. So what limitations would there be on X and Y? Well, once again, X would have to be greater than or equal to 0, and Y would be greater than or equal to 0. Okay, so these last two ask us to use that function. So we've got Y is equal to 7.2 times X, or the total area mode is 7.2 feet squared per minute times the number of minutes. Okay, so what number does the function assign to 24? Remember, functions assign outputs to inputs. So that means that 24 is our input. So that must mean what area of lawn could be mowed in 24 minutes. So I'd have Y is equal to 7.2 times 24. And so I'm going to just do that computation and find out that Y, the total area mowed, is equal to 172.8, and that would be feet squared. So that would be the area that could be mowed in 24 minutes. And then how many minutes would it take to mow an area of 400 square feet? So 400 square feet is is the area, so that would be our output. So we're saying if the output is 400, then what is the input of minutes? So we have this equation, 400, which I'm putting in for Y here, is equal to 7.2 times the number of minutes. So this means this time I'm going to have to divide by 7.2. And so here we'll see that becomes 1. And X is 400 divided by 7.2, which is 55.5, or approximately, so we'll use the approximately, 56. 56 what? So 56 minutes to mow 400 square feet of lawn. Okay, let's look at example 2 now. Okay, exercise 2 to work with. We're told this is a linear function. It has the table of values below. So volume of water is a function of the time in minutes that the hose is running, or the hose in this situation. So I'm asked to describe the function in terms of volume and time. So total volume of water is a function of the time the hose is on. So we need to write the rule that represents the linear function. And so we have a rate. We can see that 44 gallons flows in 10 minutes. So our rate is 4.4 gallons, just go gallons per minute. Okay, so my function rule here is going to be the total volume is 4.4 times the number of minutes that the hose is left on. So what number does the function assign to 250? That is, how many gallons of water flow from the hose in 250 minutes? Okay, so total volume in gallons is equal to 4.4 times the number of minutes, in this case 250. Okay, so Y is equal to somewhere around 1,000 gallons. Let's see what it is. 1,100 gallons. 1,100 gallons. Okay, so that's how many gallons of water flow from the hose in 250 minutes. Okay, so let's continue with this problem. The average pool, it says, has 17,300 gallons of water. If the pool has already been filled to 1/4 of its volume, write the rule that describes the volume of water flow as a function of time for filling the pool using the hose, including the number of gallons that are already in the pool. Okay, so first thing we have to do is figure out how many gallons are already in the pool. So it's 1/4 or 1/4 times 17,300. Okay, so 1/4 of 17,300 is 4,325. All right, so that's the water that's already in the pool. So that function should just be this, right? The flow rate is the same. So it's the 4.4 gallons per minute times the number of minutes plus the water that's already in the pool, which is 4,325. Okay, so there's our function rule right there. Okay, so approximately how much time in hours will it take to finish filling the pool? Well, we want to get the pool up to its full volume. So 17,300 is equal to 4.4x plus 4,325. Okay, so I want to just subtract the 4,325 from both sides. So if I subtract it from here, I'm left with just this x term. And if I subtract it from here, I get the additional volume of the pool that needs to be filled. So that would be 12,975 is equal to 4.4x. So now to solve for x, I'm going to divide by 4.4. Okay, so x, let's go back to purple. X is equal to, and again, remember, we can go ahead and use calculators on these. So x is approximately, because we're going to round off here, 2,948.86. Okay, so x is approximately, I'm going to round it to the nearest minute, or hours actually. This is minutes. We're going to change it into hours in a minute. So this is 2,940, and we'll round up to 49 right there. And that's minutes. sorry about that, minutes. And so to find hours, I'm going to have to divide by 60. So the time in hours would be about 40, just a little over 49 hours. So approximately 49 hours to finish filling the pool. So that would be just over 2 days with it on round the clock. All right. Okay, so we played a game with this one in class, but let's look at this here. Here we're given input and output. Now we're not told what this function is, but that it has these values. So this is a linear function, can be described by a rule in the form of y equals mx plus b, where m and b, remember, are constants. So here's a table of values. What is the equation that describes the function? Okay, so we need to know two things. We need to know m and b, and then we will have the function. Because remember, m and b are constants, y and x are our variables. There are input x and output y. Okay, so to find this equation, I want to know the rate of change. So I want to know the rate of change between any of these points. And so I can just pick an easy one here. So this output went from 4 up to 24 in a change of 4 here. So it's like finding the slope between these two. So it's the difference in y, 24 minus 4, that went up by 20, and over the difference in x, which is 4 minus 0, or 4. So I've got 20 divided by 4. My rate of change is 5. Okay, let's try another one. Let's go from these 2 points here, 10 and 11, 54 and 50 to 59. So I've got the difference in the output, difference in y, divided by the difference in x. And so that's going to be 11 minus 10. So this is 5 over 1, which is 5. Okay, just be careful. Let's do another one. So I could have 54 minus 24 over 10 minus 4. So see what I did here? The difference in y, 54 minus 24 over 10 minus 4. And that's going to be 30 over 6, which is 5. So it looks like our slope, our rate of change is 5. So let me get rid of all this. So we can begin to write our rule. Since we know that the m is our rate of change, I can write most of the rule here. Y is equal to 5 times x, because 5 is our rate of change of y with respect to x. So 5x, and so now I just need to know what b is, plus b. Well, b is that y-intercept. So the y-intercept, remember, is the point on the y-axis where x is 0. Well, they've told us what that point is. It's right here, 0, 4. So y is equal to 5x plus 4. So let's check that rule for some of these points. So let's look at this one. Y equals 5x plus 4. So we take our input, 4, multiply it by 5, that gives me 20. Add 4, I get 24. Let's look at this one. Input is 10. 5 times 10 is 50, plus 4 is 54. Let's look at this one. 11 times 5 is 55, plus 4 is 59. Okay, so now you find the inputs, or the outputs for these three inputs, 15, 20, and 23. Okay, so for 15, I'm going to have that the output y is equal to 5 times the input plus 4. So y is equal to 5 times 15, which is 75. 50 and 25, 75 plus 4, so it's 79. So I should get 79 right there. And then the next one is going to be y is equal to 5 times 20, whoops, plus 4. So that would be y equals 104. 104. And then 23 times 5. 5 times 23 plus 4. So that would be 115 plus 4. 115 plus 4 is 119. Okay, so we've filled out, whoops, the rest of that data table. Okay, so in this lesson we had some practice with using the form y equals mx plus b, and noticing that the constant rate is always the m, and the starting point, like the starting point of volume in the tub, or maybe if I'm running, I get a head start, it would be this b value, okay? And in just sort of this generic example here, that I don't know what these numbers are, this b is the y-intercept. So it's what happens when x is 0. So when x is 0, that gives me that point right there. I already knew the y-intercept for this one. Okay, so we had some experience using y equals mx plus b with these linear functions and figuring out what their rule would be, the mathematical formula would be. We saw proportional relationships and constant rates described as functions. This is a constant rate. This example here is a constant rate, but not a proportional relationship per se, because each of these ratios is not the same, because we don't have the 0.00 on our graph. Okay, so it's not strictly a proportional relationship. Okay, so we had a lot more experience with thinking of input. What is the input of a function? What is the output? And how to describe the function. So in this case, y is a function of x. We don't know what they are. In this example, total volume that flowed is a function of time in minutes. So we described functions that way. And you will do that on your problem set and exit ticket. So good luck with those. And this is a really, really important area of math. I know I say that a lot, but it is. So let's learn about functions. All right, good luck with that homework.